Your child may look at a number, say 762, and be able to tell you quite confidently that the 7 is in the hundreds place. They might even tell you it represents 700. And on the surface, it appears they understand place value. But ask them to do something that requires them to actually use that knowledge, or ask them to write a number given to them orally rather than written down, and they may struggle to do it fluently or without error. From that, a very different picture emerges. They no longer appear to understand place value. Let's pause to think about how our number system was built. In any single place, we can only ever hold up to 9. The moment you need one more than that, the place can't take it. It tips over and 1 goes into the next place to it instead. That's it. That's the whole system. So if I've got 7 in the hundreds place, that's not just a 7, it's 7 lots of 100 because of where it's sitting. Move that same 7 one place to the left, and it's no longer 700, it's 7,000, 10 times bigger. Move it one place to the right, and it drops to 70, 10 times smaller. Nothing about the digit itself has changed. It's still just a 7. What's changed is the place it's sitting in. And that place is doing all the work of telling us the value of that 7, how much it's actually worth. This is an extraordinarily powerful system. We only have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And yet, with those 10 digits alone, we can represent any number we can imagine, any number at all. That elegance didn't happen by accident. The system we use today has its roots in the work of Indian mathematicians over 1,000 years ago, and it was brought to Europe via Arabic scholars. That's why our numbers or our digits are referred to as the Hindu Arabic numerals. Before this number system arrived, Europe was using Roman numerals, a system with no 0, no positional value, and a different symbol needed for almost every quantity. Try writing the number 3,792 in Roman numerals, and you'll quickly see why the new system was considered revolutionary. The idea that the position of a digit could determine its value changed maths permanently. However, for children with dyscalculia and some children with a specific learning difficulty in maths, this notion of place value is one of the difficult things to get to grips with. Not because they haven't been taught it, but because internalizing it requires a felt, automatic sense of the size and the meaning of numbers. And that's what I want to explore in this episode. Welcome to Safety in Numbers, a podcast for parents of children who struggle with maths, including those with dyscalculia or a specific learning difficulty in maths. In each episode, we explore what might be happening when maths feels difficult and what parents can do to better understand and support their child. If you listened to episode 4, you'll recognize this as part of what we covered when we discussed numerical magnitude processing. That's the brain's ability to have an intuitive sense of quantity. If you haven't listened to that episode, it would be worth going back to it at some point because that episode and this complement each other. So why can a child know the labels and still not understand the value? The answer goes back to what I mentioned a moment ago, magnitude processing. Understanding place value isn't just about knowing the names of each digit's position. It requires a genuine felt sense of the difference between 1, 10, 100, and 1,000 as actual quantities, not labels, but as amounts. And for a child whose magnitude processing is less secure, those quantities don't automatically feel different from each other in the way they do for most people. Think about it this way. Most people know without having to calculate that £1,000 is a lot more than £100. They don't need to count up from 1 to know that. The difference feels real and immediate. That automatic sense of relative size, that felt difference between quantities, is what allows place value to make sense from the inside rather than just the outside. For a child with dyscalculia, that automatic sense may develop differently or remain less secure. The labels of the columns can be learned, ones, tens, hundreds, thousands, but the quantities those labels represent don't necessarily carry a felt meaning. And when the quantities don't feel different, the positions that represent them don't feel meaningfully different either. The 7 in 762 and the 7 in 7,620 look identical on the page. For many children, the different positions signal genuinely different quantities. For a child without secure magnitude processing, that signal may not be triggered as readily. This is also why the difficulty compounds as numbers get larger. In the early years of school, children work mainly with ones and tens, and then hundreds. These are numbers they encounter in everyday life. Prices, ages, distances, house numbers. Even without fully secure magnitude processing, that daily exposure gives children some anchor for what these numbers feel like. But as the numbers grow into thousands, tens of thousands, hundreds of thousands, that everyday exposure drops away sharply. Most of us don't handle millions of anything on a regular basis. We don't have an intuitive feel for what a million looks like or how it compares to, say, 100,000. And for a child whose magnitude processing is already less secure, larger numbers become increasingly abstract and disconnected from any felt sense of quantity. And then there is the direction that's often even harder, the smaller one, decimals. Tenths, hundredths, thousandths. These are quantities that are rare in most children's everyday experience. The name tenth is actually very informative if you think about it. It means the whole one is divided into 10 equal parts, and 1/100th is 1/10 the size of 1/10. The pattern is entirely consistent with everything we've already said. Each step to the right of the decimal point is 10 times smaller, just as each step to the left is 10 times larger. But that consistent pattern requires exactly the kind of magnitude understanding that dyscalculia affects. For a child without a secure felt sense of how numbers scale, the decimal system can feel entirely abstract. This is why you might notice that your child manages reasonably well with smaller numbers, but becomes far more confused as numbers grow larger or when decimals are introduced. In these cases, it isn't a new difficulty now appearing. It's the same underlying difficulty becoming more visible as the demands increase. So what does all of this actually look like for a child in practice? Because I think once you see it clearly, a lot of things that might have seemed puzzling about your child's maths start to make sense. I want to tell you about a boy I assessed. He was 9 years old. bright, engaged, clearly well taught. When I asked him what the 7 and 762 represented, he said immediately 700s. No hesitation, perfectly correct. Later I asked him to write the number 3,792 in digits, and he wrote 3,000,792. I want to give you a moment to consider that. He'd written 3,792, a number with 7 digits, not 4. And when I asked him to explain his thinking, he said, quite matter-of-factly, I know that thousands has 3 zeros. He had a rule, and the rule was partially right. There are indeed 3 zeros in the number 1,000 written on its own. What he'd not yet connected was what 1,000 represents as a quantity, why the position of each digit changes its value, and how the number he had written differed from the one I had asked him for. The label 700s and the rule thousands has 3 zeros was sitting in his mind as two completely separate pieces of information, neither of them connected to a strong sense of magnitude. Now, that's not a failure of effort or intelligence. That is a child who has learned to navigate the surface of place value without access to the understanding beneath it. You may also recognize this pattern in a different context, when your child is doing a written calculation that involves exchange. You might use the terms carrying or borrowing. These procedures depend entirely on understanding what happens when you move between positions. 10 ones become 110. 110 can be broken back down into 10 ones. 10 tens become 100, and going the other way, 100 can be exchanged for 10 tens. This principle of exchange underpins almost every calculation your child does. When a child doesn't yet have a secure, felt sense of those relationships, exchanging, that's carrying and borrowing, becomes an arbitrary step to follow rather than logical consequences of how the number system works. And arbitrary steps followed without understanding are exactly the kind of thing that doesn't stay in the memory. You might notice your child following the procedure correctly one day and losing it the next, not because they were careless, but because there was no deep understanding anchoring it in place. I've watched many children work through a column addition where they need to exchange, and you can see the moment the procedure breaks down. They follow the first steps correctly because they've memorized the sequence. But then something goes wrong. They might carry the wrong digit, forget to add what they've carried, or write it to the wrong column. And when you ask them to explain why they did what they did, they can't, because there's no understanding anchoring that procedure. There's only a half-remembered sequence of steps. The most useful thing you can do at home to help your child build a felt sense of place value is to use physical objects. The reason is directly connected to everything we've talked about in this episode. Abstract written digits don't automatically carry meaning for a child whose magnitude processing is less secure. The 3 in 300 looks identical to the 3 in 30. Only its position or place tells you its value. And if you don't have a secure internal sense of how different those values actually are, that positional information doesn't connect in the way it's supposed to. Physical objects give the brain a different route to that understanding, not through abstract symbols, but through real, tangible experience of quantity. There is a set of equipment widely used in primary schools and not expensive to buy that is designed specifically for this purpose. It's named after Zoltan Dienes, a Hungarian mathematician who spent much of his working life in England. He believed passionately that children learn mathematics best through physical, hands-on experience. He died in 2014, aged 97, so not that long ago, and his influence on how maths is taught in primary schools is still felt today. You might hear the equipment referred to as Dean's apparatus, or base 10 equipment, or base 10 blocks. They're all the same thing. The pieces come in 4 sizes: a small cube for ones, a rod for tens, a flat square for hundreds, and a large cube for thousands. And the size differences between them are real and proportional. I'll put a link in the show notes so that you can see exactly what it looks like. When a child holds a small cube representing 1 in one hand and a large cube representing 1,000 in the other, and feels and sees the difference in size, they are experiencing physically what 1,000 times bigger actually means. That experience is something that abstract digit manipulation cannot provide. And the exchange principle we talked about in the last section becomes real in a way that it never can on paper. When a child takes 10 of those small ones cubes and swaps them for a single tens rod, and can hold the rod in one hand and the 10 cubes in the other, the equivalence stops being a rule to remember and becomes something they have experienced with their own hands. Your child's school almost certainly has a set, and it's worth asking whether your child is using them during maths lessons as regular support when undertaking addition and subtraction. Alongside the blocks, squared paper is a surprisingly useful tool for place value. Give your child some paper split up into squares and ask them to colour 1 square to represent 1. Then colour 10 squares in a row to represent 10. And create a 10 by 10 block of squares to represent 100. Suddenly, the relationship between 1, 10, and 100 is visible right there on the page, and your child has made it themselves, which can support their understanding. You can take all of this in the other direction too, into decimals, with a simple activity that children often find satisfying. Start with 1 cube made out of Play-Doh or blue tack or similar, representing the 1 whole. You may wish to keep it the same size as the base 10 cube representing ones. Then divide it into 10 equal parts. They're going to be small. Each part represents 1/10. Then take one of those parts and do your best to cut it into 10 equal pieces. Each piece is 1/100th. If you want to go further, your child may imagine that one of those hundredths can be cut into 10 more to represent thousands. The point of the activity isn't the cutting, it's the seeing, it's the experiencing. A child who has physically made a 10th and a 100th has felt that sense of those quantities that no written explanation can replicate. Another resource knowing about is place value counters. These are small counters, a bit like coins, and each of them has their value written: 1, 100, 1,000, and they also go the other way, where you can have 1/10th, 100th, and 1,000th. Unlike the base 10 blocks, where the size of the piece shows you the relative magnitude, the place value counters are all the same size. The value is written on them rather than it being built into their shape. They're particularly useful when working with decimals, where the Dean's pieces become very small and fiddly. Your child may well use these at school alongside base 10 equipment. Your child will also be familiar with a place value chart from school. It's a grid with columns labelled ones, tens, hundreds, and so on, where digits are placed into the correct column or place. It's a useful tool, and your child probably uses one regularly. I mention it here simply so you know what it is if your child refers to it, or if you see it in their school book or on a worksheet they bring home. It can be useful as a reference point for understanding the approach their teacher is taking. And if your child is using one at school, it's worth knowing what it looks like so you can make sense of what they're showing you. I've linked one in the show notes. Now keep the activity you do with your child short and use the same pattern each time. Make the number, say the number, write the number, and compare the three representations. For example, 372 can be built with 3 hundreds, 7 tens, and 2 ones. Ask your child to describe what they have made, and they will say 372. Get them to write 372 beside it. That makes a connection for your child. You may later on, once they're confident with that, change one part and ask what has changed and what stayed the same. Asking questions such as, how do you know? Can you show me another way? Or what would happen if we exchanged these 10 ones? They reveal more than a page of practice questions. What the base 10 blocks and the blue tack activities have in common is that they make magnitude visible. The size differences are built into the materials themselves. Place value counters work differently, but used alongside a place value chart, they can give a child a concrete way to organize and manipulate values that might otherwise feel abstract. For a child who hasn't yet developed a secure, felt sense of quantity, physical experience is the most direct route to that understanding. Using materials isn't a step backwards. It's where building understanding begins. I've put together a companion guide to go alongside this episode. It's a free PDF, and you'll find the link in the show notes. It pulls together the representations that I've talked about today so that you have something concrete to refer back to when you need it. In the next episode, we're going to look at what you can do when you are worried about your child's maths. Thank you for being here. If you found this episode helpful, please do share it with another parent who might need it. And if you'd like to make sure you don't miss future episodes, you can subscribe wherever you listen to podcasts or follow the Safety in Numbers YouTube channel. Until next time, thank you for listening.